without gravity it would move straight. With gravity, it's being pulled in and it goes in a circle. The equation F is equal to ma, right? We did this a few times. We know F equals ma. We know that F is equal to the constant. We're talking about a geosynchronous satellite, so a satellite going around the Earth. So the two masses are the mass of the Earth and the mass of the satellite, divided by the distance between. What is this distance? RES?
Between two masses.
Between the two, meaning from the center of both masses. So it's the center of the Earth to the center of the satellite. If the satellite is small enough, we don't really care because the distance is so big, another meter or two is not going to make a difference. But it's from the center of the Earth to the satellite. Okay? Now, this is equal to ma, right? Which m? Was that? Okay, he says mass of the Earth times what? ma times acceleration of what? Acceleration of the satellite. So this says that the force on an object, or the force between the two objects, is equal to this stuff. What does this say? Okay, this is not correct.
No, it's the mass of the satellite.
Okay, why mass of the satellite? We could do this. Mass of the Earth times acceleration of the Earth. There's a force between the two objects, right? And we can say the force on one of the objects, let's say the Earth, is equal to the mass of the Earth times acceleration of the Earth. Or the force between the two results in an acceleration. The force between the two equals to the mass of the satellite times acceleration of the satellite. But you can't mix the two. Okay, the force on an object equals to its mass times acceleration that results from that force. Okay, so the force here, you have a force between two objects that's created, and it reacts on the two objects. So you can put MEAE or MSAS. Okay, so it's important to put in the subscripts to know what it is. Clearly, whichever M you put here, that M will cancel out. If it's ME, it'll cancel out with this. If it's MS, it will cancel out with that. So you're going to be left with GRES squared with one of the M's over here. Is equal to the A corresponding to whichever that is. If it's a circular path, which it usually isn't exactly, but let's say it's a circular path. Now, because it's moving in circular motion, what can we say? Anything moving in circular motion, we derive the formula. We found that the acceleration is equal to v squared over r. All right? So we can do a shortcut. Instead of just a, we already know that it's going to be the magnitude of the velocity squared over r. Now, which r is this? What does this r mean?
Radius of the circle.
No,
Radius of the circle.
Radius of the circle in which it's moving.
Yeah.
Okay? So it's equal to v, the velocity, tangential velocity around the circle, divided by the radius of the circle. Now, does that relate to anything over here? Is this r the same as any of these quantities? Okay, why is it different than this r?
That's the radius from the satellite to the Earth.
To the, not to
Center
the
of
Earth,
the
to the
Earth.
center of the Earth.
Yeah.
Okay, and what is this?
That's around.
Okay,
Around
here's
the
the
Earth.
satellite. Here's the Earth.
Yeah.
So r, little r, is this.
And the other Earth.
And which is the other r?
Around.
Okay, so it depends. R, okay.
Oh,
Is r this? This is the Earth. This is the height above the Earth. It's actually, the truth is, the height of a satellite is not very much compared to the radius of the Earth. So if you have, this is the Earth, the satellite is moving like that, even less. Okay? So big R is that this is from the center of the Earth to the satellite.
Same thing.
What is little r? Little r is the radius of the motion of the satellite. What is the radius of the motion? Is this the radius? Is this r, the radius of the motion of the satellite? If that were the case, that means the circle would be like this. So what is little r, the radius of the satellite's motion, circular motion? It's the same thing, it's big R. Okay, so this we can now say is equal to big R. RES. It's the same R. You don't put it in immediately. You have to figure out which r it is. It turns out to be exactly the same r because it's the distance from the center. Okay, so now obviously one of these r's will cancel out. Okay. Now, what does geosynchronous mean? Geo, Earth, synchronized. Okay, synchronized with the Earth. In other words, it stays over the Earth at any one. It stays at one particular point over the Earth. It's a satellite, let's say, hanging over Manhattan. Okay, so as the Earth turns, it has to turn with the Earth exactly. Okay, so what does that tell us? What quantity in here will it tell us? The fact that it revolves around the Earth with, let's say, staying over Manhattan. Velocity of?
Velocity of the Earth's rotation.
The velocity of Earth is the velocity of the sun.
They're moving with the same velocity. Now, why is that true, though? Isn't, let's say, if I look at the satellite, let's say over here, let's say this is the Earth. The Earth is rotating, here's the satellite. Let's say this scale. Are they moving with the same velocity?
No.
Why?
The satellite's smaller.
More why? Say it?
Satellite gotta go around more
Yeah, you gotta go fast.
It's going a much larger distance
to keep up.
than, let's say, Manhattan Island is traveling around in space, covering this distance in 24 hours. This is covering a much greater distance. So if it's covering a greater distance in the same time, then obviously it's going much faster, right? Moving like this, at the same, it's constantly over the same point. So this one covers a small circle in 24 hours. It covers a big circle. This one's going much faster. But if they're very close, then it's approximately equal. This is 4,000 miles and this is 100 miles or something. Right? So it's approximately equal, not totally. If we didn't want to assume it exactly, so we would make a little adjustment. Okay, but if we know that it's very close, then we can just assume, at least in the beginning, that it's about the same. All right, so what is that speed? If it's moving at the same speed as Manhattan going around in space, so how fast is Manhattan revolving in space?
One rotation for a day.
One rotation for a day. So we have, how much is one rotation? What's the distance that it covers? If this is r, it's 2 pi r. Right? Covers it 2. So the velocity is equal to distance over time, 2 pi r per day. Okay? We can just, let's call it t because we use the word, the big T, remember, is the period of revolution in the circle. So where t is 1 day. So t is 2 pi r over t. Right? So now we can substitute that inside here. All right? We're going to get 2 pi r over t, so we're going to get an r squared. The r squared, one of them cancels out with 0, we're going to get an r, and that's going to make an r cubed at the bottom. Basically, at this point, we already have the answer, where v is equal to 2 pi r t over t. All right, the rest is just plugging in the number. Let's do it over here. Okay, so we have ms. So what is v squared equal to?
2 pi r.
Well, it's 2 pi r over t squared. So it'll be 2 pi r over t squared, right? Over r ds. Where what is this r? Which r is this?
The same one.
Same r. It's 2 pi r is this r. Okay? So it's big r, 2 pi r. Which is equal to what? ms. 2 gets squared to 4. The pi gets squared to square. R squared over r t squared. Okay? Just everything. All right? R squared over r. One of the r's cancel. Okay? So if I just bring this to this side and this to this side, what do I get? I get MEMS over r squared is equal to this, where this is the same r. R or 7. Okay, what's going to happen here? The ns cancels out. Right? One of the masses is always going to cancel out. This is going to cancel out with this. What's going to happen with the r's?
One will cancel.
One will go on that side. Okay? And you'll have t squared on this side. Okay? What would you say? How much is g mass of the Earth, this remains, right? G mass of the Earth doesn't get canceled out. Okay, equals 4 pi squared, what? What's over here? Again? R cubed over t squared. This is actually an important equation. You see how we got that? We had F, the force between the two objects, is equal to the mass times the acceleration. Acceleration is v squared over r. V is 2 pi r over t. One of the ends cancel, right? Obviously, this end is going to cancel. This end cancels, this end cancels. We get 4 pi r squared r over t squared. GME, we move this r on this side, will be r cubed over t squared. You don't see that?
You write it out.
Well, you have GME ms over r v squared, okay, is equal to mv squared over r. Just by cross multiplication, GME, right, move this up to the top, right? Cross multiplication of A over B equals C over D. A equals C D over D. This is equal to this and this over that. This is equal to this times that over that. Okay, so here you have r squared, here you have r squared will be r to the 4, r will be r cubed. Okay, so you can go over this maybe more leisurely at home, you have r cubed over t squared. Okay, so G and E, now this is G times the mass of the Earth, where the mass of the satellite canceled out, right? The mass of the satellite is not in here. So obviously I can do this for any satellite mass, okay? What I find basically is that this is a constant. G is a constant, the mass of the Earth is a constant. That means this is a constant. That means that the radius, the cube of the radius over the square of the time that it takes to go around a circle is a constant. A planet and its moon, or the sun and a planet, right? I could have done mass of the sun times mass of Earth, and over here, mass of the Earth. So I have the Earth going around the sun, right? And this leads to one of the things that Kepler discovered, Kepler's laws. And you can use this very nice little equation to come up with all kinds of interesting ways of measuring, let's say, if you see another planet, and you know how long it takes to go around in a circle around the sun, which is easy to see by astronomical observation, you can determine, right, if you know t, you can determine the radius. So in other words, you can look at a planet, see how long it takes to go around the sun, or how long its year is relative to yours, right? And then you can find out the distance. Without knowing its mass, all you have to know is the mass of the object that's pulling it, namely the sun. Okay, so it's a very nice formula. It's not a more basic formula than everything else. It comes out of F is equal to ma, where F is equal to this. And where you know that the acceleration is v squared over r. Just canceling and moving things over, you get to this. Okay, we spoke about weightlessness. If you drop a scale, if the scale reads 0 and you drop it, all the while it's falling, it's going to read 0. Right? There's no reason that it should say something while it's falling. It's only if the screen is present. If now you take an object that weighs a lot and a scale, and you drop them both, which one will fall faster? Scale weighs 10 pounds and the object weighs 100 pounds. Which will weigh faster? Which will fall faster? The same thing. They fall at the same speed, the same acceleration. So one doesn't press the button. If you jump off the table, that's what the example I gave last time. Let's say you attach a scale to the bottom of your feet and you jump off the table. As you're in the air, you're not pressed against the scale. So the scale is not going to read anything at all. So it's as though you have no weight. Of course you do have weight. It's just you're not pressed against the scale, so the scale is not going to show your weight. An object in an elevator at rest exerts a force on a spring scale equal to its weight. Okay? The elevator is standing still, so obviously it doesn't matter that's an elevator, it's just like you're standing on the floor. Your weight and the normal force are equal. The floor is pushing against the scale is pushing against you. W equals mg. Nobody's moving, no unbalanced forces. B, in an elevator accelerating upward at a half g, the object's apparent weight is 1.5 times larger. Okay? The sum of the forces are not zero. The sum of the forces is equal to mass times acceleration. Okay? And the acceleration is 1/2 g. So you have to do W minus mg is equal to m times 1/2 g. Okay? And if you solve that, we'll find out that W is equal to 3/2. In a freely falling elevator, what's happening in a freely falling elevator? You're not pressing against the scale at all, right? The scale is falling and you're falling and the floor of the elevator are falling. So you're not pressed against anything. They're all falling with the same thing. It's like strapped to the bottom of your feet. As you're falling, you're certainly not squeezing the scale. So the scale is not reading anything at all. Okay, this moves in like that. If this is moving really fast past the Earth, when it's far away out over here, it doesn't experience, let's say, when it's a parsec away, it's very, very far away, a light year away, it's not going to experience really gravity. R is so big that basically the force is zero. It gets closer and closer and experiences the gravity more and more. It starts curving in towards the Earth. If it's going fast enough, although it's curving in, it'll curve more and more and more in, but it's going so fast that it escapes. Okay, it's curving in, it's curving in, it's curving in, getting closer in, but it never quite hits, and then it's getting further away, so the gravity force is getting less and less, so it stops curving in and it escapes. If it's going at a certain speed, not quite as fast as that, it curves in, curves in, curves in, curves in, and it's declining. Okay? If it's going in at just the right speed, what will happen? It'll be moving like this, but it'll also be falling in, so it curves in. It'll be moving forward. There's nothing stopping the forward motion. There's no friction in space. And it's also falling in, so it moves like that. It's still moving forward, but it's also falling in, so it moves like that. Go on a chair with the scales attached to your feet, and as you're falling, look down at the scale until you land. For that half a second that you're in air, there's not going to be any weight, right? You're weightless, or you're not weightless. Okay, it's exactly the same thing. I jump off this table onto the floor with the scale attached to my feet. I won't see any weight until I hit the ground. What did we see about motion where the acceleration is always directed towards the center? That's circular motion, right? It's moving like this. The acceleration is in towards the Earth. 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 Okay, the combination of sideways motion plus acceleration towards, there's no acceleration in this direction, it's a constant speed in this direction. But acceleration in this direction, acceleration in this direction, acceleration in that direction, due to the force in that direction, gravity, causes it to move in a circle. So you'll have an orbit. All right? Now, clearly, gravity is what's causing this acceleration towards the center. Gravity is causing it to orbit instead of moving off like that. So clearly, it has weight. Gravity is pulling it constantly. It's constantly falling in to the gravitational source. It's falling. It's always falling in. But because it has the sideways speed that's exactly matched, it doesn't have to be that way. It could have so much speed that it escapes. It could have not enough speed and it crashes in. In some cases where the speed is exactly matched, it falls in. It's constantly falling in towards the gravitational source. It's falling. But this motion saves it exactly enough so that it doesn't ever actually get closer. So it could be falling in towards the Earth but never getting closer. That's what happens with any satellite. So the Earth going around the sun is falling into the sun. We are falling into the sun at this moment. But we're also moving tangentially fast enough that it exactly compensates. So we're not getting closer to the sun. Of course, we're not exactly in a circle. We're in an oval. So we are getting sometimes a little bit closer, a little bit further. But basically, consider it, let's say, as an approximation, as a circle. We're not getting closer to the sun. A satellite, the moon going around the Earth, is falling into the Earth all the time. It has a weight. It's falling into the Earth, but it's exactly compensating. A satellite around the Earth, the same thing. Now, when you're falling, right, if you're falling, you have no weight in the sense that if you put a scale under your feet, the scale is also falling with you. So your feet are not pressing on the scale. You're both just falling together. So you're standing on a scale, you're falling down, and you say, oh, I have no weight. Yeah, of course you have no weight because the scale is falling just with you. But if you're in orbit, right, you're inside, let's say, the spaceship going in orbit around the Earth, the spaceship is falling into the Earth, and you are in the spaceship falling with the spaceship. So both of you are falling into the Earth. If there's a scale in the spaceship, you're standing on the scale. You and the scale and the spaceship are falling into the Earth with the same acceleration, and therefore your feet are not pressing into the scale, and your feet are not pressing into the floor of the spaceship, and therefore you feel you don't have weight. If you now push against the bottom of the spaceship like this, if I do this, I fall right back down, right? I have weight. The weight pulls me down. If I do this in a spaceship, what happens? Will I fall right back down?
No.
Why not? Well, what will happen is, if I'm pushing up, we're falling like this. I'm pushing up. So now I have a speed, right? Before I was just falling with this. Now I give myself a speed relative to this. So what happens is I simply hit the roof of the spaceship. But I'm still falling. I'm falling the whole time. So I am falling. I'm falling now, and if I'm in the spaceship, I'm falling. And if I push against the floor, I'm still falling with gravity, but I gave myself a speed relative to the spaceship, so I hit my head in the spaceship. So in the spaceship, I push up like this, and I move up with that speed, right? With that speed up to the roof, by pushing against the roof. So it looks like I'm floating weightless. I'm not floating weightless. I have weight. I'm falling down. I'm constantly falling down. I have weight. But I would need to take a scale that's not falling to show my weight. You can't take a scale and fall with it and say, I have no weight. You can do that here. You can, you know. Okay, so that's satellites and weightlessness.